No, Che, don't get too close to the railing. That's dangerous. Dangerous like trying to use a single reference method for a bond breaking process. Yes. Now, now, now. There, that's better, isn't it? Yes. Let's talk about non-dynamical or so-called static electron correlation. So there's two types of electron correlation. A lot of times we refer generically to electron correlation, and generally we mean dynamical correlation, but there's a different kind, non-dynamical correlation. What do all these terms mean? Let me illustrate this with an example. I'm showing you the correlation energy for the water molecule in a simple double zeta basis set. This was a famous paper of Harrison and Handy published in 1983, where for this double zeta basis set they were able to solve the electronic Schrodinger equation for a given geometry exactly within the given basis set. So it's a full CI calculation, and the difference between the full CI energy and the Hartree-Fock energy is the correlation energy. And they observed something really interesting. At equilibrium geometry, so if I minimize the geometry of the water, I get 0.148 Hartrees of electron correlation. And if I stretch the molecule either to 1.5 times or 2 times the normal OH bond lengths, the correlation energy gets bigger in magnitude. So there's a bigger difference between Hartree-Fock and full CI. And the reason this is surprising is that if you imagine the electrons distributed in a water molecule, they should be spread out in space, hanging around the nuclei of the water molecule. And if I stretch those OH bonds, I effectively have more volume in which to put those electrons. And that means they should have less of a hard time avoiding each other through the R12 operator. And so electron correlation energy should become smaller in magnitude as you go to bigger and bigger bond lengths, because I've got a bigger molecule to spread those electrons out. And this electrons avoid each other at close range kind of effect we call dynamical correlation. And we're pretty confident that that should get smaller at larger bond lengths. And so there must be some other non-dynamical kind of electron correlation happening at these larger bond lengths. Okay, so just to recap, the correlation energy is the difference between full CI and Hartree-Fock, and we saw that got bigger in magnitude for the stretched geometries, which was a surprise. So there has to be something besides this dynamical correlation effect that we're missing in Hartree-Fock. What else are we missing? Well, we're missing the fact that as I stretch bonds, I have electron configurations that become more important or closer in energy to the dominant Hartree-Fock reference electron configuration. And that is a new kind of consideration that we have to account for. And that gives rise to so-called non-dynamical correlation. So let me go through a little bit of the mathematics to try to illustrate where this is coming from. And I'll try to make the example as simple as I possibly can. So let's start with the H2 molecule in a minimal basis. So there I'm going to have a 1s function for atom A and a 1s function for atom B, and that's it. So of course, if I combine those two orbitals in phase, I'll get a sigma bonding orbital, and the atomic orbitals are not orthogonal, so their overlap is S12, and that's going to go in the normalization factor. And then, of course, the other combination is the minus combination, and this one will be an anti-bonding orbital. And if I have two atomic orbitals going in, I have two molecular orbitals coming out. One is stabilized, that's the sigma orbital, and one is anti-bonding and destabilized. And I can form a Slater determinant, and of course I'll use the Aufbau principle and fill the lower energy orbitals first. So the sigma orbital is the lower energy orbital, and I can put two electrons in that one. I'll put an alpha spin electron in it. I'll call that phi sigma. And I'll put a beta spin electron in it. I'll call that phi sigma bar. And so here's my 2x2 Slater determinant. Remember, in a Slater determinant, your orbitals are the columns. So the first column is spin orbital sigma with alpha spin, and the second column is spin orbital beta sigma with beta spin. And the rows are the electrons. So row 1 is electron 1, row 2 is electron 2. And if I were to expand out the determinant, I'd see I have both ways of putting those electrons in that orbital. Electron 1 is alpha and electron 2 is beta, or vice versa. And if I switch them, I get a sign change when I expand the determinant. Okay, great. Let me do that. Let me expand the determinant. So a 2x2 determinant expands this way. And here, as you see, I've got electron 1 with alpha spin and electron 2 with beta spin, and then vice versa, where I've swapped them, and anytime I swap these for fermions, I should get a minus sign, and I do. So this is all totally fine. Now what I'm going to do is plug in the formulas I had earlier for phi sigma and phi sigma bar, and here I'll use restricted orbitals, so those are actually going to be the same spatially. And what do I get? Well, I get my normalization factors out front, and I get phi A plus phi B for electron 1, that's this guy, and then this one is phi A bar plus phi B bar for electron 2, and then I get a minus sign. And then I have the sigma orbital, the positive combination for electron 2, and then I have the sigma orbital positive combination for electron 1. All right, and I can rewrite this, if you want, this way, where I have quite a few terms, and you can trace through that math and check that if you like, but I'll move on. And I'm going to say I can collapse that previous slide into a simplified notation where I'm going to go back to a Slater determinant form, but now I'm making a Slater determinant where the columns are atomic orbitals rather than molecular orbitals. This is a little bit of a weird thing to do, but this is a little easier to visualize. And I get a normalization constant out front. So my molecular orbital version for the Slater determinant can be rewritten as a sum of 4 Slater determinants made out of atomic orbitals in this case. And here I see I put the electrons in phi A, that one s orbital on atom A, and the same one but with a beta spin, or I mix them up and put one electron in A and one on B, and vice versa, one in B and one on A, and then finally both electrons on atom B. And in each case, each determinant has one alpha spin and one beta spin. That's good, so I haven't messed with the spin. Now, I'm going to assert that this way of looking at the determinant shows you that there is a problem with this determinant if I go to long bond lengths. At equilibrium, it's totally fine, no worries. But if I go to long bond lengths and this is my Slater determinant, there's a problem. Why is that? Well, this term and this term put both electrons on one side of the molecule or the other. So this phi A bar puts 2 electrons on atom A, and vice versa, phi B bar puts 2 electrons on atom B. And that's a problem because at long range, that's not reasonable. At long range, I should break my HH bond, and I should have 1 electron on the left on atom A and 1 electron on the right on atom B. But the first determinant and the second determinant show me that I have ionic contributions where I have H negative and H plus, or vice versa, H negative and H plus. And those 2 terms shouldn't contribute at long range, but they do because they're part of the Hartree-Fock determinant. And so restricted Hartree-Fock in general won't work for bond breaking processes if you go to long distances. And then I'll just illustrate that with this graph. So I'm showing you a plot of the energy for restricted Hartree-Fock in green versus full CI in black. And full CI is the exact solution within this basis set. And this is just STO3G, a minimal basis, just to keep it easy, like in my mathematical example. So the exact result is in black, the RHF result is in green, and you can see at short range, there's a decent agreement between these two, and it's not bad. But as I stretch the bond, I get a much bigger error, and then the error is just enormous at long bond lengths. And it's because I have contributions from these ionic configurations where I put 2 electrons on one side or the other, and that is very high in energy and shouldn't happen at long range. So this RHF energy is way too high at long bond lengths. In fact, if I do some manipulation of the terms, or if I think about the so-called quasi-classical interpretation of Hartree-Fock energies, you might remember each electron gives me a 1 electron term, which I might call H sigma sigma, because it's just a sigma orbital. And there's 2 electrons, and if it's restricted orbitals, these will be identical, so I'll just call it 2 of these guys. And for a single pair of electrons, all they can do, if one's alpha and one's beta, the most they can have is a Coulomb interaction J, and I can call that J sigma sigma, and that's really it for a 2 electron system. But if the bond length gets really large, what I ought to have is that the energy ought to go to 2 times the energy of a single hydrogen atom. What's the energy of a single hydrogen atom? Well, it's just a single H term. There's no J terms, there's no K terms. So in this case, it ought to turn into, in terms of atomic orbitals, HAA plus HBB, and at infinity, A and B are equivalent to each other. It doesn't really matter. And the sigma orbital at infinity will turn into this. We could do a little math and show that, but I'll just assert that's what you get using manipulations kind of like I had on the last couple of slides. The cross terms will go away, and I just get this guy. So that's fine. My first term in the RHF energy at long range becomes the energy on atom A and the energy on atom B, which is what it should turn into. So this is good. But then the RHF energy also has this J Coulomb interaction, the repulsion between the electrons, which should go to 0 at long range, but it turns out it doesn't. And so this is why you're getting an error in the RHF energy, is because I'm overestimating the energy because I have this term that ought to go to 0, but it doesn't. This is a different way of saying those ionic configurations contribute. All right. You could also look at this in another way that I'm a fan of, which is to say that the problem is I have electron near-degeneracies. In fact, they become exact degeneracies as the distance between the nuclei goes to infinity. And I ought to account for that in some way, but I'm not accounting for it. So remember, Hartree-Fock has exactly 1 Slater determinant in it, and the reason we do that is we assume there's 1 electron configuration that's important. But if I have the H2 molecule and I go to infinity for the bond length, there are actually 2 electron configurations that are just as important as each other, and I'm forced to pick only 1 in RHF, and that's my problem. What are these configurations? Well, the sigma squared configuration, I put both electrons in the sigma orbital. That's the low energy one. That's pretty obvious. We like that one. The problem is at long range, because the electrons get so far apart from each other, whether I have a sigma orbital where these 2 are in phase, or a sigma star orbital where these 2 have different phases, it no longer matters if they're so far apart they're not talking to each other. So the sigma star squared configuration is equally good at infinite distance. And I have 2 configurations, and I'm forced to only pick 1 of them, and that's a problem. Both of these have the same energy as RAB goes to infinity. So what I really ought to do is somehow mix these two determinants with each other and account for both of them. Do I have a way to do that? Well, sure. The simplest approach is configuration interaction, where I write the wave function as a linear combo of two determinants. I've got one determinant where I put both electrons in the sigma orbital. That's the one we talked about for RHF. And now I'll mix in a second determinant with some weight, C2, which puts both electrons in the sigma star configuration. And you might say, well, why don't I include one electron in sigma and one electron in sigma star? For a minimal basis, that one can't contribute by symmetry. That one would have a so-called Ungerada symmetry to that wave function, and so those determinants don't contribute if we're looking for the ground state, which is a Gerada state. All right, so these are the only two I need for a minimal basis, H2. And I can do a configuration interaction calculation. The energy is just the expectation value of the Hamiltonian for this wave function. So I can plug this in matrix form and write this out and see that I get this combo of terms. H11 will look like the Hartree-Fock energy. H22 will look like the Hartree-Fock energy if I pick this configuration, which is higher in energy, unless you're at infinity, in which case it's the same as this energy, H11. And H12 is going to be a mixing term, and it's this mixing term that lets CI lower your energies. If CI only had terms like the first two, mixing in a higher energy thing would never help you. But the energy is a weighted sum of the ground state, Hartree-Fock determinant, higher energy determinants, but these mixing terms that make it favorable to do the mixing. Now, what are these matrix elements? Well, I could use Slater's rules, which I talk about in electron correlation notes. And we've already seen that H11 is just the Hartree-Fock energy of the ground state determinant, where I put both electrons in the sigma orbital. H22 is the analog of that, where I put both electrons in the sigma star orbital, which is in general higher, but will be the same at bond lengths of infinity. And these coupling terms, these determinants differ by two spin orbitals. So Slater's rules tell me that I get a matrix element. I work that out in physicist notation and get a double bar integral. Then I do spin integration and convert to chemist notation, and I wind up with this guy. It's electron repulsion integral over spatial orbitals that mixes sigma and sigma star. And I could plug all of these values into the previous equation for the energy and do a little bit of math and see that I get this. So here's my Hartree-Fock energy for both electrons being in sigma. Here's Hartree-Fock for both electrons being in sigma star. Here's my mixing term. And then if I plug in what is the sigma orbital for this very simple example, it's determined by symmetry as just being a plus combination of the two atomic orbitals, or sigma star, a minus combination of the two sigma orbitals, of the two atomic orbitals. And then the mixing integrals vanish as RAB goes to infinity. Then, after a little bit of math that I'll skip the steps, the CI energy is just the energy of an electron on atom A plus the energy of an electron on atom B, which are equivalent, if the CI coefficients are the minus of each other and equal to 1 plus or minus 1 over square root of 2. And this is great because I said that if I get the exact solution at infinity, the energy should be a simple sum of the energy of this guy and the sum of the energy of this guy. And that's what I get in the CI. So CI, because it allows some mixing, essentially cancels the overestimation of the J sigma sigma term, which is good. And because these coefficients are equal to each other, I essentially get a 50-50 mix of the sigma squared configuration and the sigma star squared configuration, which is really good. The weight of a determinant in the CI expansion is basically the square of the coefficient. So if I square this coefficient, if it's plus or minus, it doesn't matter, the minus sign will cancel, I get 1 over 2. So it's half of the first one and half of the second one, which makes sense if they have exactly the same energy and they're exactly as good as each other. Great. So you might say, well, let's just do CI on everything. And that would work great if you do the full CI and include all possible determinants, but we normally can't afford that. So then we run into some problems. The other thing is that I need to determine the orbitals correctly. In my minimal example, the orbitals fall out from symmetry. They have to be plus and minus combinations of the atomic orbitals. In larger basis sets, that no longer is true. So how do I get my molecular orbitals? Well, really, I should find good orbitals that minimize the energy of the entire wave function, the CI wave function, not just a single Slater determinant. So I want unbiased molecular orbitals. The ones I usually get are biased towards the particular electron configuration I choose for the Hartree-Fock. So I need a way to do that, and we'll talk about how to do that in a minute. It's called MCSCF. Even if I do MP2 or CISD or CCSD or CCSD Princess T, and I use the regular RHF orbitals, or even if I try to use fancy orbitals, I can get methods that just fail for any kind of bond breaking, which is really disappointing. So let me show an example of the BH molecule. Here I've picked a large basis set just to show you that picking large basis sets doesn't solve anything. Let's start off at the top with restricted Hartree-Fock in blue. I get a curve that might look okay to you if you didn't know what the right answer was, but the right answer is the black curve. That's full CI in this basis set, and it's way different. And you notice a couple things. First off, the blue curve is shifted way up compared to the black curve. Now, in principle, this isn't a disaster because chemistry is all about the shapes of curves and the differences between one point on a curve and another point of a curve. And it's less relevant if the entire curve is shifted or not. So if the blue curve were just a shift of the black curve, it would actually be fine. I'd get the same bond length, I'd get the same vibrational frequencies, I'd get the same dissociation energy. But in fact, I get a very different dissociation energy. Why? Well, the dissociation energy is the energy difference between the energy at the minimum of the well and the dissociation limit. And you can see that here for full CI, it's about so high or so. And in the blue curve, it's way higher than that. The dissociation energy is massively overestimated. Why? Because the RHF energy is going way higher than it should because of the contribution of these high energy ionic configurations to the wave function. So the blue curve is really not just a simple shift, but the dissociation energy got way, way too high. So this RHF curve is kind of a disaster. Can I fix it with MP2? Because that introduces some electron correlation. Well, the correlation pulls the curve way down, so I get this pink curve. The energy is very stable compared to the RHF curve, so that's good. You're still a little off from the full CI, but the problem is I don't stay parallel to the full CI. I do till about here maybe, and then the energy goes too high, and then it does this terrible thing where it starts turning over, and if I were to keep going, it would go down, 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 down. So this is no good. Coupled cluster, singles and doubles, the red curve is about the best of the ones I'm showing you. It's very parallel to full CI at equilibrium and near equilibrium. And the error gets a little bigger out here, and then it tracks, it stays a little bigger. So it's not great because it's not perfectly parallel, but it's sort of reasonable, especially on the scale of this curve. CCSD Princess T is the so-called gold standard of quantum chemistry, and you would expect it to do the best, and it really nails it around equilibrium. It's even closer to the full CI than CCSD, so it's great until about here. And then some disaster happens, and the energy goes way low, and you get just garbage out here. Why is that? Well, it has something similar to do with the problems of MP2. They're both suffering from the fact that they're relying on perturbation theory. MP2 is a perturbative approach, Moeller-Plesset perturbation theory. CCSD Princess T uses perturbation theory to estimate the effect of triples. And that perturbation theory is breaking down at large distances. CCSD has no perturbation theory in it, or if it does, it's taking it through infinite order. So it's more resistant to these problems. So this is one of the rare cases where CCSD is actually better than CCSD parentheses T in a case of bond breaking. Why is perturbation theory bad? Well, it's very easy to see just from this simple formula for the MP2 correlation energy. Your correlation energy, the correction to the Hartree-Fock energy, is a sum over quadruplets of orbitals, 2 occupied orbitals, I and J, and 2 virtual orbitals, A and B. I get this 2-electron integral in the numerator squared divided by an energy difference, the energy difference between the sum of the virtual orbitals that the electrons are exciting into minus the occupied orbitals that the electrons came out of. And you can imagine, say back in H2, if I get to long range, those sigma and sigma star orbitals become degenerate. This also is true for BH or any single bond breaking. If I go to infinity, whether the orbitals in the atomic orbitals are in phase or out of phase no longer matters because they're so far apart. So sigma squared becomes degenerate with sigma star squared, and this is a spin orbital expression. If I have 2 electrons corresponding to the sigma orbital, sigma alpha and sigma beta, and if I have 2 electrons corresponding to sigma star, alpha and beta, they'll all become degenerate, and this denominator goes to 0. And I have a negative energy correction, so I divide by 0, the energy crashes down to negative infinity. And we started to see the beginning of that on the previous slide for BH, and if we were to keep going to larger distances, it would keep crashing down. So I really can't treat the sigma star squared electron configuration as a small perturbation, which is the assumption of perturbation theory. It's equally important as the sigma squared configuration. Just to show a different example, this is the torsion in the ethylene molecule. And I'm just showing the 2 p orbitals that combine to form a pi molecular orbital. And if they're in phase, that's good. So that's a bonding orbital, a pi orbital. Now imagine I'm twisting the molecule where I keep one CH2 unit fixed and the other one I'm going to rotate. If I get up to 90 degrees, that's exactly in the middle here. And you see that I've kept the left-hand CH2 the same, and then the right-hand one is now pointing at me. And then if I were to keep twisting this, I would actually hop up this way and land up here, where the left orbital looks the same as it did, and the right orbital now flipped 180 degrees, and I'd get here. But this is no longer a bonding orbital. This is an anti-bonding orbital. And so I don't want to put my electrons in an anti-bonding orbital. So it's higher energy, and I don't. So at 180 degrees, it's identical to 0 degrees. And I could denote this by flipping the sign on this orbital. But if I flip the sign of an orbital, it doesn't have any consequence. This is just another picture of the same thing as this guy. So I want to stay on the potential curve that keeps me in bonding orbitals on the left and equivalently on the right. And but in between, it's neither bonding nor anti-bonding. And the issue is if I were to follow this orbital kind of adiabatically, I wind up in an anti-bonding orbital, which is bad. So I don't want to do that. So my potential curve has kind of an avoided crossing here and looks like this if I get the accurate curve. But look at this 90-degree situation again. This one, I have another way of drawing this orbital, which is this one, and this is not just a sign flip, because notice the right-hand side is the same. Blue's pointing at me and red's pointing into the page. So it's not a sign flip from top to bottom, but this other way of drawing it is equally as good, right? This is exactly as bonding or anti-bonding as this one. There's no way to tell one of them is better. They're not equivalent anymore, unlike this one and this one. And so I really, at 90 degrees, need a combination of both of these guys to describe what that ethylene looks like at 90 degrees. And if I only have one determinant, I'm unable to do that. So if I have one determinant, I try to stick to this one, and then right at 90 degrees, what am I going to do? Well, I'm going to do some kind of flip over to this picture because I want to avoid going up here. And so I get a discontinuity where on this side it looks like this picture, on this side it looks like this equivalent picture, and in between I have to have some hop of solutions, and it looks discontinuous. And that's exactly what I see. If I plot, say, the restricted Hartree-Fock energy, I get a discontinuity as I'm hopping between those two equivalent pictures at 0 and 180, and I get kind of a spike in between. If I do MP2, it doesn't fix it, I still have a spike. If I do CISD, it doesn't fix it, I still have a spike. If I do CCSD, it doesn't fix it. If I do B3 lip, if you like DFT, it doesn't fix it. So none of these approaches fix it. There's only one nice curve on this plot, the CAS-SCF curve, and we'll talk about what that is in a minute. Now I can kind of cheat. So far I've been using restricted Hartree-Fock references, restricted orbitals, and that's appropriate because I have, in all these cases, closed shell singlets that ought to be able to use restricted orbitals, so that seems appropriate. However, I can kind of cheat if I go ahead and use unrestricted Hartree-Fock references. And then especially if I do dynamical correlation on top of that with the post-Hartree-Fock method, I can get some decent energies. You have the disadvantage that your spin properties are all garbled up. And at dissociation, you have a 50-50 mixture of singlet and triplet, which is really not correct. But your energies can look okay. Technically, you have to trick the programs into finding this lower energy UHF solution by mixing HOMO and LUMO or something like that. And this is not a cure-all. Your energies are not perfect. They're better, but they're not perfect. So let me show you what happens. Here's the same BH example we showed a minute ago, but now with unrestricted orbitals. Now the energy levels off with Hartree-Fock in a very nice way. MP2 gives me a better correlation energy, so I'm closer to the exact full CI answer. CCSDs, the red curve, looks pretty good. I get a little error here in this intermediate region. So notice I do great at dissociation. I do great near equilibrium. I have a little trouble in between. Sometimes this is called the spin recoupling region. CCSD Princess T, the gold standard, pretty good. It has a little trouble here, but it doesn't go crazy at long distances, so that's good. So in general, these are improved. You notice there's a little bit of a funny wiggle in the MP2. That's easier to see if I go ahead and show you the errors. So now I'm plotting errors for restricted curves in solid symbols and unrestricted curves in open symbols. And you can see that in general, the unrestricted curves have problems in the intermediate region. So MP2 goes a little crazy in the intermediate region here, and it has a constant error of about 15 kcal here and constant error of about, 12 kcal here, and it spikes up in between. That's not great, but it's better than the restricted case where the error goes from 15 way up to like 55 kcal per mole. So it's not at all parallel to the full CI curve, and that's pretty terrible. And then it starts crashing down here. If I look at Hartree-Fock, the restricted one is way off, and it's not parallel, and the energy goes way up. Unrestricted, it comes back down, but I have this kind of mess in between. CCSD is not bad. It's the red curves, and you can see that I make a little bit of a mistake for unrestricted CCSD in the middle, but at long range is perfectly fine, and at short range is perfectly fine. And similarly for CCSD Princess T, little trouble in between, but it's pretty flat, unlike with restricted orbitals where I have this big error at long range. That was just one example for BH. Let me show you a summary table that tells you how this works across several molecules. The first three are all single bond breaking situations. And the next one is the C2 molecule, which has a double bond, so it's a little trickier. And notice I'm plotting the non-parallelity error, which is the difference between the maximum error and the minimum error along the curve. So it tells you how parallel is the curve, and we want these to be ideally about 0. That would mean a curve that's exactly parallel to full CI, which would be perfectly fine. None of them are exactly parallel. CCSD has non-parallelity errors from about 8 to 13 for the single bond breaking and 24 for C2, which is pretty bad. Unrestricted MP2 is not very good. Unrestricted CCSD is a lot better, but I still have multi-kcal errors, and it's really bad for C2. CCSD Princess T gets you within about 3 to 4 kcal non-parallelity, which is not great, but it might be okay, depending on what you're doing. And for C2, it's still terrible. C2 is just very hard if you're going to try to break 2 bonds at once. And B3-lip, unfortunately, will not solve things for us. Let me show my twisted ethylene example again, just to show if I do unrestricted Hartree-Fock, this pink curve, I get a nice smooth curve, so it's no longer discontinuous at 90 degrees. So that's really good. I'll also show you a so-called 2 configuration SCF. So I weight those 2 important determinants exactly equally, and I get a nice looking curve. Compared to this one, the UHF is a little too shallow. It's not quite right. And then I have CAS SCF, which we need to talk about in a minute, in blue, which looks great. And then in red is a valence optimized orbital couple cluster approximation to that Anna Krylov and I looked at with Martin Hedgordon sometime in the past. All right, so non-dynamical correlation is what's going to account for these near-degeneracies. And how do I include that in my wave function? Well, my wave function really ought to include all electron configurations that are nearly degenerate, and in principle it really ought to include them with an equal footing as my so-called reference Hartree-Fock determinant. How can I do that? Well, you could imagine a scenario where instead of doing a Hartree-Fock based on 1 Slater determinant, I could do a Hartree-Fock based on 2 or 3 or 6 or 10 or 20 Slater determinants and find the orbitals that minimize the energy of that combo of determinants. And if you do that, that's the idea between multi-configurational self-consistent field, MCSEF. You find the optimal weights of the determinants using a configuration interaction type approach, and simultaneously you find the best set of orbitals for that combo of determinants instead of for a single determinant. Now, in general, people don't generally do MCSEF calculations because it's too tedious to pick out the most important 8 or 10 or 50 determinants by hand. Instead, people go ahead and pick some set of orbitals, molecular orbitals, they'll call them active orbitals, and they'll just do all possible determinants that can be formed in that set of orbitals. And that's called complete active space self-consistent field. And that is much easier to do than picking out a whole bunch of different determinants. Now I just pick some set of active orbitals. This will give you a sort of Hartree-Fock quality wave function if I am modest about the number of determinants that I pick. But it still doesn't really account for the dynamical correlation. It accounts for the non-dynamical correlation. So to account for the dynamical correlation as well, I could do some multi-reference CI, multi-reference perturbation theory that could look like CAS-PT2 or NEV-PT2, or multi-reference couple cluster. There's a whole series of methods that I won't really explain in detail, but I'll just mention that these are all various ways to get both the non-dynamical and dynamical correlation, and they tend to be computationally expensive. So back to this twisted ethylene example, CAS-SCF, now I've defined it, you see that it gives a nice smooth potential curve and it looks pretty great. It does recover a lot more correlation energy than the minimal description of non-dynamical correlation that I get from the 2 configuration self-consistent field. Now, just to compare and contrast single reference methods versus multi-reference or multi-configurational methods, the top group of rows shows you single reference methods and their non-parallelity errors, again in kilocalories per mole for these different test sets. And then the bottom group is various multi-configurational approaches, CAS-SCF. CAS-PT2 adds MP2-like dynamical correlation on top of the CAS-SCF wave function. CISD bracket TQ is something I played with as a grad student. It's a particular flavor of multi-reference CI. And second order CI is another flavor of multi-reference CI, where you do essentially a full CI in the active space and then all single and double excitations out of the active space. This would be a very, very complete multi-reference CI. And you can see the second order CI is by far the most accurate approach looked at. This bracket TQ is almost as good except for C2 where it's not. CAS-PT2 looks pretty good. It's one of the better ones. It's not as good as multi-reference CI in general, but it's more affordable and it's reasonable. CAS-SCF by itself is not great because it needs some correction for dynamical correlation. Unrestricted CCSD parenthesis T is not perfectly parallel to the full CI. It's reasonable. It's a quality similar to CAS-PT2 for BH, not as good for HF, not as good for H4, and definitely not as good for C2. And the other ones have various qualities that may or may not be good enough depending on what you're doing. So let's talk about this active space. I've mentioned that CAS-SCF takes all the determinants in a set of active orbitals rather than having to enumerate separately all the different determinants by hand. So how do I pick this space of orbitals that I'm going to use to generate my list of important determinants? Well, what I'm going to do is if I did know what all the important determinants were, I would compare them all. And I would say, okay, as I look across my list of all the important determinants, which orbitals ever have their occupation change? So if I have, say, 20 important determinants, and I see that a certain molecular orbital is doubly occupied in every one of those, that doesn't need to be in my active space because it doesn't change. It's not active, it's inactive. But if I look at my important list of 20 determinants and I see sometimes this orbital is doubly occupied, sometimes it only has one electron in it, maybe sometimes it has 0 electrons in it, if its occupation changes across the list, that's an active orbital and I need to include it in my active space. The only problem with this concept is that the way I've just described it, to know what the active set of orbitals is, I have to already know what the important determinants are. But it's kind of a chicken and egg problem. I'm trying to find a way to automatically generate the list of important determinants given a choice of orbitals. And so how do I know what set of orbitals to pick to get a good set of determinants? It's not necessarily obvious. There are some schemes proposed in the literature for picking an active space. And these are easier for the user if they can just have a rule that says, well, I'll always pick this set of orbitals. Then that tells me what to do and I don't have to spend a lot of time investigating it. Unfortunately, there isn't necessarily a clear-cut scheme that's always best in any kind of situation. And there are a number of proposals in the literature for automating this process, but I'm not sure that any of them yet have been widely adopted. So this is a situation where just having some prior experience is a good thing. Let me just outline some possible strategies so you get an idea of how people could go about this. Here's a water molecule, here's a molecular orbital diagram. In water molecule, it's a C2V molecule. So the irreducible representations are A1, B1, A2, B2. You occupy 3 A1 orbitals, a B1 orbital, and a B2 orbital. If I choose a valence space, I pick all the valence orbitals. I don't include the 1A1, that's a core oxygen 1s, so he's not valence, so I don't include him. These are all valence occupied orbitals, and the valence space would consist of 2 more orbitals as well. So a valence set of orbitals would be all of these guys, 4 occupieds and 2 unoccupieds. I could pick what's called a 1-to-1 choice. That says pick 1 active virtual unoccupied orbital for every active occupied orbital. And if I pick the valence orbitals as active occupied, then I pick a similar number of active inoccupied, and I'll keep the symmetries if I have symmetry. So here I've got a A1, another A1, so two A1s, a B1 and a B2. So my one-to-one space would add a virtual A1, a virtual B2, a virtual B1, and another virtual A1. So I have 4 active occupieds, 4 active virtuals, and they have the same number of symmetry irreps as each other. And finally, I can pick what I will call a minimal active space, which is just only the orbitals necessary to describe the bonding or anti-bonding orbitals for the process I'm describing. And here what I'm going to do is I'm going to actually rip both hydrogens off of the water molecule, and that involves breaking 2 sigma bonds, and those sigma bonds in the symmetry labels would be an A1 orbital and a B2 orbital. So those are part of my minimal occupied space, and then the virtual space in this case is a virtual A1 and a virtual B2 as well. So that one's the smallest choice. It has 4 orbitals compared to larger numbers for some of the other ones, up to 8 orbitals for the one-to-one. We did a little study in 2005 looking at some multi-reference methods to see how effective they are with these different choices. I'll outline some of the results really quickly. Here's CASPT2, which is probably one of the most popular multi-reference methods out there, with these 3 different choices of active space, one-to-one, valence, or minimal. And here's second order CI, which is essentially the most complete multi-reference CI you can do. If you do CAS active space, full CI in the active space, and all singles and doubles out of that. Some people will call that a multi-reference CISD. And I'm plotting the error as a function of the bond length, and you can see that these are pretty flat compared to the single reference methods we looked at, so they're all kind of good choices. The down triangles are the second order CI, the multi-reference CI, they have the smaller errors than the CASPT2. It's also more expensive to do this, so that makes sense. If I do the second order CI, it doesn't matter particularly what active space I pick. The one-to-one is the biggest active space, so it has the smallest error, but it's pretty parallel to the full CI, and these are not much worse in terms of parallelity, so any of these are okay. For the CASPT2, there is some superiority in this particular example for the one-to-one active space, which is the bigger active space. None of these are perfectly parallel, not as good as the multi-reference CI, but not bad for the one-to-one active space. There's a little bit more non-parallelity for the other 2 active spaces. So your active space can matter. It will matter less the more complete treatment you do. If you do a fancy multi-reference CI, it'll matter less, perhaps, than if you do a CASPT2. This is a table summarizing some of our results for different unimolecular bond associations or triple bond association in the case of N2. And I won't get into any details other than to say second order CI, multi-reference CI, tends to have smaller non-parallelity errors. CASPT2 is next, and CAS-SCF has the biggest non-parallelity errors because it doesn't have any dynamical correlation. And sometimes certain choices of active space are better than others, and it kind of depends on the molecule and the method what that you're doing, how much difference it makes how you choose the active space or which one is better. There's not a universal best choice. So let me wrap up. Bond breaking and bond making reactions are tough because unless you go to full CI, which is unaffordable, or a fancy multi-reference CI, which is usually unaffordable, it's hard to describe these accurately, especially if you go to the dissociation limit. If you're at just a normal run-of-the-mill transition state and you're not doing a clean break of a bond and then going off to infinity, your problems will be similar to the ones I've described, but reduced in magnitude. So you might be able to get away with CCSD Princess T for a transition state that starts to break and form bonds at the same time. That's not as challenging as a clean break of a bond that goes off to infinity, fortunately. Anytime electron configurations become degenerate or nearly degenerate, a multi-configurational or a multi-reference approach is really the most appropriate one you should do. And whether this is strictly required just depends on how high accuracy you need for your application. Sometimes you may be able to cheat and get by with an unrestricted Hartree-Fock reference. If you don't care about the spin properties, you may get energies that are adequate depending on what you're doing. And certainly this is an active area of research. I haven't mentioned a lot of cutting edge methods like DMRG or various approaches that try to reduce the computational cost of doing the full CI in that active space for a CAS-OCF. There are approaches out there that make that more affordable, and so it's more easy to do multi-reference CI or CAS-PT2 or CAS-OCF on larger molecules thanks to these cutting edge methods. And that's all I'm going to say about multi-reference approaches. I hope you have an idea of what they are and some idea of where to start if you might need to use some of these in your own research.